Good morning, everybody. Nice to see a lovely big audience. And we're very pleased to welcome back Alan Costley. He has done several presentations on nuclear fusion over the course of his time at this course, starting in 2014 with "Do we need it and is it possible?" And I think he'll show that actually it's moved on a bit since then. He's a trained physicist and he's worked in fusion for the bulk of his professional life. This talk today is particularly about fusion and developments between the East and the West. So is it East and the West, or is it East against the West? So his experience is particularly pertinent to this, as it includes leading a small team working on a UK-USSR project in the 1970s at the Kurchatov, I apologize for the pronunciation, Institute in Moscow, one of the Soviet's main nuclear research labs. He has worked in multiple fusion labs in Europe and the US for 8 years at the main National Fusion Lab in Japan and 16 years in a senior position on the International ITER project. Since the 1980s, he has had an association with the Academy of Sciences of the Institute of Plasma Physics, Hefei, China, where he is a senior advisor on one of the most advanced fusion devices in the world that is being constructed there. He brings his wide experience to an attempt to answer the question, is it East and West or East versus West? Thank you.
Well, thank you for the introduction. We've had a few difficulties with the setup, so hopefully it'll run smoothly from here. As was said in the introduction, and as I said in the blurb that I sent in for the talk before, I'm going to look at this. I'm going to look at the latest developments in fusion, but also from an East plus West or East versus West. And the question will become obvious as we go through the talk perspective, because the East and West dynamics of this have always been important, and if anything, they're more important even now, as you'll see as we go through. So I'm actually going to start at a basic level. We look at the brief early history, and then I would like to look at the tokamak device, which is the most successful fusion machine to date, and I'll show you some impressive results on the progress that's been made. And then I'll look at the joint. This is the East plus West endeavor, which is embodied in the ITER project, the International Thermonuclear Experimental Reactor Project, a very large project under construction in France. I will look at some parallel approaches which have emerged recently, many of them privately funded by investors. And then we'll go to that question, is it East plus West or East versus West? And there is definitely a race in progress, and who's going to win them? And then as some concluding remarks, I'll try to go beyond, look further forwards. Right, so now I'm going to start really early, like 10 to the minus 10 seconds after the Big Bang. And I thought I would start very early to tell you where fusion energy comes from, because it's very, very basic, it's primordial. So 10 to the minus 10 seconds after the Big Bang, all that existed was what are known as quarks, gluons, and electrons, and they're a very high level of energy. So it was far too energetic for anything to fall. And the universe expanded at an incredible way. Space itself expanded. It wasn't the universe expanded, it was space itself. It was a very difficult concept. But the consequence of that was that it started to cool down, and it got to the point where the quarks and the gluons could come together. The gluons, as they name it, are like a sticking force, and create the fundamentals of nuclei, that is protons and neutrons. So after about a second, you've still got this tremendous energy. It's obviously much bigger now because of the expansion of space, but it's protons and neutrons and electrons and a lot of energy. But we then have to wait. So we then have to wait another 3 seconds before nuclei themselves start to form. And what happens is that the protons and the neutrons come together to form nuclei, and the electrons remain free. Now, in that process of creating nuclei from the free protons and neutrons emerges the binding energy, which is the energy which binds them together. So some of that energy that existed went into binding the particles together. I can see better without. And then about 380,000 years later, we had the formation of the atoms. Basically, they're cooled enough for the electrons to be able to be captured and atoms to exist. And then, of course, after that, we've got the stars coming from gravity and then creating the elements in the stars. So at this point, the energy in the atom is locked in the binding energy inside the nucleus. So it's very interesting. Look at that again. So here we have protons and neutrons, which generally are called nucleons, and they're held together by this binding energy. Now, if you plot, and this is a very instructive plot, if you plot the binding energy per nucleon, so we take the binding energy divided by the number of nucleons in the nucleus against the atomic mass, if you like, the number in the nucleus, you see a curve here where the binding energy per nucleon is highest roughly in the middle, and that's where you find iron. At this end, you find the heavy elements like uranium and tungsten and so on, and here the lighter elements like hydrogen and helium. And when you have in nuclear fission, the nucleus a heavy nucleus breaks apart, and it breaks into smaller constituents, and the energy leaves on this, and the binding energy of the product is less than the binding energy that was there in the first place, and the difference is the kinetic energy on the parts that have come apart. And now, so that is fission, which is breaking apart, and fusion is going in the opposite direction, where you take light elements and you try to fuse them together to bring them to a more stable nucleus. So here we have two isotopes of hydrogen, tritium and deuterium, bringing them together to go to helium and then a neutron. And if you look at the binding energies in the helium, obviously there's no binding energy here, that is less than the binding energy there. And that difference in binding energy is taken away mainly by the neutron, 80% by the neutron, 20% by the helium. And it actually can't, and if you add up the masses here, so the masses here, you'll find that there is a mass difference. These actually weigh a little bit less than they did. So a little bit of mass has been converted into a little bit of energy. And just to give you, and because of the, as you know, from Einstein's famous equation, E equals mc squared, because of that small amount of mass that's gone into energy, you get a lot of energy. And just to give you a number which you're going to find incredible, but the amount of mass that was changed into energy, which generated the atomic bomb little boy that was dropped on Hiroshima, 165,000 ton equivalents of TNT. That was 0.7 of a gram. So if you can convert 0.7 of a gram into energy, that's the kind of energy you need. So that's one of the reasons we're interested in fusion, because there's a lot of energy. So the basics are, it's clean, it's abundant, fuels are light as isotopes of hydrogen, it's safe, and I'll explain why that means later. I mean, the fusion reactors just want to turn off naturally. They don't, no chance of runaways, and the economics, the predictors say are convective. Now, we need to look at some more basics here. In order to make fusion work, we have to be at a very high temperature. And as you take any material and you heat it up, it goes from solid to liquid to gas, and then into the plasma state. And for fusion, we need temperatures in the region of 100 million degrees. And at that temperature, all products, as you say, as I said, the numbers involved with this are just mind-blowing. You have to be in the plasma state. Now, plasma is an somewhat unfamiliar state on the Earth because most is solid, liquid, gas. But within the universe, something like 95% of matter is actually in the plasma state. Of course, our sun is one big plasma. But also we get examples, lightning plasma ball for fun, and lightning. These are examples of plasmas. Now, plasmas it's a very special medium, far from your normal experience. The density of molecules in it is very low, and has a very low mass. For example, a typical jet plasma, which is produced in the large fusion device in Cullen, has got about the weight of a postage stamp. On the other hand, the temperatures are high, 100, 200 million degrees, and the speed of the ions, as you can see from these numbers here, very high, 1/10 of the speed of light. Now, because of what's known as a long-range Coulomb force, they attract one another by the electrostatic force, which is a long range. It means that any particular ion or electron is interacting with a million others. So that makes it very complicated to study. And that has led to the statement it's a very complicated medium. But fortunately, these charged particles stick to magnetic fields. If you have a magnetic field and a highly charged particle, it basically sticks to it, usually in a spiral motion. The plasmas are very complex with multiple interactions and over a temporal and wide temporal and spatial scales. However, it can be contained in magnetic fields using that. And this leads to the subject of plasma physics, which is a discipline all in its own right, and thousands of people work on that throughout the world. Now, jumping now to how the most successful device we created to hold the fusion plasma together is a tokamak. And basically, what the problem, if you just used a straight magnetic field and you had your free particles connected to it, you would lose them out the end. So what they did is they take the magnetic field and put it into a toroid. But it turns out to be that even that's not enough, and you need an additional field. So that's basically what we've got here: a linear field running in that direction, and then another field running in that direction, and the two add up because magnetic field is a vector quantity, so you end up with a spiral going in a torus. And that's essentially what a tokamak is. And that's been the most successful device, tokamak configuration. And that's what it looks like in practice. So here is your magnetic coils. There is your plasma carrying a current, which is induced with a transformer. And this is an example of one. This is the jet tokamak at the Cullen Laboratory. That's a picture from the inside, and that is a schematic from the outside. Now I'm going to skip over the next slide because there's a video on there and it might cause trouble. Oh, it actually wasn't too bad. This is not too bad, is it? No. This is a jet tokamak plasma. This side here is so hot you can't see it because it's radiating away from the visible region. The light you see comes from the interaction. 2 seconds. The sound was auxiliary equipment going on in the jet machine itself. So I'm going to move to the very early history, and this is where we start to see the interactions of the east and west. In the very early days, there were suggestions to try to develop controlled fusion, as it was known then, in the early 1950s, and initially in Russia, but shortly afterwards in the UK and the US. So they were the main players. Early devices did not give good results. They were too leaky. Basically, the energy just leaked away. In 1953, Eisenhower addressed the United Nations, and he proposed the peaceful application of nuclear energy. And this led to the creation of the IAEA, the International Atomic Energy Authority, and a willingness to exchange information and results during the Cold War. And at the first Atoms for Peace conference in Geneva in '58, no great progress on fusion was presented. But then, about 10 years later, the Soviets turned up saying that they had produced a device, which they called T3, tokamak 3, which could produce 1 million degrees, so into the right range. But nobody believed them because their measurements did not look secure enough. Now, in parallel, and something happened in the UK, which at the time was a big embarrassment, but actually was a moment of serendipity. And that was that in the UK, there had been great embarrassment because on their fusion device, which wasn't a tokamak, but it was close, you can see the toroidal nature of it, called Zeta, Zero Energy Thermonuclear Assembly. They had got results, this is in Harwell, 57, which they thought were fusion. And Sir John Cockcroft, leader of the endeavour, said he was 90% sure that measured neutrons are caused by fusion. And this generated headlines like that, a son of our own. But unfortunately, it turned out they were wrong. And the neutrons were in fact due to an artifact in the plasma, high energy electrons striking the vacuum vessel. They were nothing to do with fusion at all. So the British, embarrassed by this, they developed this very fancy measurement technique where they take a laser, pass it through the plasma with very high power laser, and they look at the radiation scattered by the particles within the plasma and measure they send in a single frequency, they measure the spectrum of the scattered light, and basically by using the Doppler effect, they're able to determine the temperature of the plasma. And so they've got a good temperature measurement, which was just what the Soviets needed, but didn't act. And so this led the director of the Kurchatov Institute in Moscow, which was essentially the Moscow, the Soviet equivalent of Harwell. Give you some idea how secure it was. He said that he called it a brilliant development, and he invited the director of Cullen, Baz Pease, to send the technician and the scientists, the technicians, and all the equipment to put on their T3 to show the world that indeed they had achieved fusion. And that's what happened. A team known as the Cullen 5 went, and they proved that they found the Soviets were in fact correct. And that went on to lead to a worldwide explosion, because at that point, many labs around the world very quickly built tokamaks. And then in the late 1970s, another British team followed up with a more novel technique to measure the full spatial profile of the temperature. So here is what's known as the Cullen 5. That's a picture of their device on the T3 tokamak. And here's the Cullen 3, or the UK 3, in about 8, 9 years later. And you might recognise somebody there. In those days, I had some wrap over hair, and I was probably wearing bell-bottom trousers. So that is the very brief history, and then it exploded worldwide. Now, we need a number to measure our progress. And the number we use is the fusion triple product, which is the product of density, temperature, and energy confinement time. And the fusion power gain, to get for fusion power, you need this number to be bigger than that number there, right? So there's a threshold. You've got to get density, temperature, energy confinement time. Now, energy confinement time is the time which the energy is held in the plasma. For example, your hot water tank has got that energy confinement time. If you turn off the power, the temperature will slowly go down over 12 hours. That's the confinement time, energy confinement time of your hot water tank. Well, plasmas are the same. So that's density, temperature, and energy confinement time. We've got to get it right up there, and we need temperatures in the 100 to 200 million degree range. And if we do that, we find there's a simple relationship between this parameter called Q fusion, which is the ratio of the fusion power you get out relative to the fusion power, the energy the power you have to put in to make it work. So that's a simple ratio, Q. Got to be bigger than 1, otherwise you're not winning. That is a number I'm going to be coming back to again and again. Fusion power produced divided by power needed to make it happen. And if you look at the progress that was made between 1960 and about 2000, it was absolutely tremendous progress. This is a log plot here. These are orders of magnitude. It's fantastic. And here's the T3, here's the beginning. This is American one here, and then the German jet, the color. So this by no means a full list right up to jet. Now these are upgrades on the various machines. We're almost there. And then international politics entered, because Gorbachev and Reagan had a summit which basically agreed nothing except to collaborate on fusion power to build the next device and to get above Q equals 1. That was 1986. And so here were all the cross-section of all the fusion machines in the world, and they decided to come together to build this very big device, ITER, which the modeling suggested will get way above Q fusion 1, possibly 10. They created the international organization, International Thermonuclear Experimental Reactor, originally the US, Russia, main players, Europe and Japan, and then later, much later, 10 years or more later, South Korea, China, and India joined. So 7 partners. And this is when it's under construction now in France. And this is what it looks absolutely enormous. There's a person there, give you some idea of the size. And here is the plant. This was a year or so ago. The fusion plant, a kilometre or so, at least in maybe 1.5 kilometres in each direction. It is enormous. And to give you some idea, it's a very high cost. Hard to estimate the cost because the way the project is put together, the components are sent from the different parties. So China's making the coils and Europe's making the vacuum vessel and so on. So the costs are individually in the individual parties. As you can imagine, that leads to very difficult interface problems. And to give, this is one of the toroidal field magnets. Look at the size of that. You see the size of people in there. And the weight is enormous. The weight of one of those coils is roughly the same as the weight of a fully loaded 747. Now, this is what has happened to the project. So originally, it was supposed to start building in 2006 and be first operational in 2016. But for very reasons I've already hinted at some, it got delayed and delayed and delayed. And these are the reasons. The original estimate was far too optimistic, but the management structure that was set up had the wrong priorities. It was all about getting the politics right, not about getting them fit for purpose right. In-kind procurement, as I've mentioned, a weak central team. I was in the central team for 16 years. We almost had very limited budget. It was all coming from the parties who kept control. But we had the job of trying to make it fit together. Delayed, there were technical problems. There was the French regulator, as overseeing, lost confidence in the project, got hit by the COVID pandemic, of course. So now we're in a situation where it still hasn't turned on. The first plasma is expected to be something in the region of 2030, 35, something like this. And with fusion, not until approaching 2040. So that's what happened to our wonderful picture. Tremendous progress, and ITER right now here. It just stopped the international progress. Now, fortunately, there are other ways to do fusion. I mean, I've mentioned the magnetic approach here, but there's another approach using high-powered lasers, and there are others as well, magnetic traps and electrostatic traps, various other inventive ideas you can bring this plasma together. And I'll just say a few words on the laser. In the case of the laser, basically you have a very, very small capsule, only a few millimeters across, and you bring the high intensity laser beam in from different directions, from all these different directions, carefully balanced, and create the conditions. That's give you some idea. This is the scale of that's the capsule. It sits inside of what's known as a hologram, about 1 centimeter. And these are the various tools used. And that's what it looks like. That's what the lab looks like. That's the lab with the lasers in it, roughly the size of 2 football pitches. And then here inside is the light pipes gathering the laser light and then bringing it to a focus in there. So that's the laser approach. Now, what happened in the intervening period, as I showed you, between about 2000 and 2020, there was this big gap. But technology hasn't stood still, of course. Many things have been developed, and there's a lot of work been going on basic R&D. So this leads forth to what we call faster fusion, which is alternative approaches, including private companies. And there's at least another 2 new major government initiatives. So Government programs in general, why has this happened? They've been overwhelmed by the cost overruns of ITER. But some new physics has emerged and technologies. Investors with deep pockets have arrived looking for somewhere to put their money because oil and gas, of course, are going out of fashion on a 30 or 40-year timescale. And finally, we got this realization that we really do need fusion as a potential for application is huge. And the role that was a birth, there was a birth of at least 35 individual private companies during this period. Massive increase in investment. Now, I'm going to talk briefly about 6. Starting with Commonwealth Fusion Systems, which is a tokamak, moving to tokamak energy, which is a tokamak of a sort, and then going to one which isn't a tokamak at all, but aims to simulate it. And then a very different one, this is a laser-based system, and then it leads to a linear pinches. So we need to come back to this number again, this NT tau number. If you do some physics on it, you find that it depends on the size squared, the magnetic field cube, and what's known as a shape factor. I'll come back to that in a minute. So if you want to go up in NT tau, you can either increase the size, which of course is what EAT is doing, or you can increase the field, which is what the next device is doing. I'll show you that, or you can change the shape, which is what tokamak energy is. So here's the next device. This was a company spun out of MIT called Commonwealth Fusion Systems, and they're working on a device called SPARK. Smallest possible, affordable, robust, and compact. And it is a small tokamak, but with a very high magnetic field, 12 Tesla in the plasma center, which means something like 24 Tesla on the coils. And they've had a lot of money invested, probably more than any other private one, something like 1.8 billion, including the likes of Bill Gates and ENI, which is interesting, because that's an oil firm. And they're making great progress, as I will show later. Now, the key point is that they use high temperature superconducting magnets, which is a new technology. I'll say a little bit more about that later. So that's what it looks like. And there's the site. And that's what it looks like on the inside. And they've even got plans all the way up to a reactor. This is their next device, which is called ARC, the reactor, affordable, robust, and compact, something like that. And although they're clearly a little bit behind, because when they made this slide, they were preparing Spark to turn on in 2025. It's not, it's going to be a bit later, but I'll show you later. So the key thing about this approach is it uses what are known as high temperature superconductors. Now, you will have heard of superconductors. That is, if you cool a conductor low enough, it'll eventually have zero resistance and you can pass power over very long distances. It can also withstand magnetic field. But high temperature superconductors, in order for low temperature superconductors to work, you have to get close to absolute zero. But high temperature ones work right up to liquid nitrogen temperature, 77 Kelvin, so much more feasible. So that is the Commonwealth Fusion Systems approach. Now, a little bit more on shape. As I mentioned, the shape of most tokamaks is more like a donut. But you can also squeeze it up and make it look more like a chord apple. That's known as a spherical tokamak. And we can define a couple of parameters, A, which is the major radius, maybe the minor radius, and the elongation, which is how peak is. And if we go back to that equation, here we go. So that's the field. We've talked about the size of the field. And if you go very elongated, small a, then you can produce what's known as a chord apple type approach, which is what Tokamak Energy have done, which is a private company spun out of Cullen, working on the Milton estate near Didcot. And they've combined the spherical tokamak approach with high temperature superconductors, the ones I mentioned, and they've come up with a recipe towards fusion power using smaller devices. They have an experimental device, a recent picture with all the ancillary equipment. And they have achieved great things. For example, they have achieved temperatures of 100 million degrees. And I'm actually, I used to be a consultant for this company, but then I left. And then they asked me to chair an external international committee to basically validate these measurements. They were kind in their publication to acknowledge OC, and we basically check what they've done to confirm they are roughly 100 million degrees. Now, remember what I said, to make a tokamak, you need a magnetic field going in a toroidal shape, and then ideally, so you achieve that by applying a magnetic field like this to make it go like that, and you drive a current, which gives a field around the current, so you end up with a spiral. So that field is achieved by making an external field and with a plasma's own current. However, you gain more control if you could make externally a twisted magnetic field. This generates what's known as a stellarator. And so it ends up being rather complicated magnetic field, as you can see. But the benefit is you have full control over all the magnetic fields. So you don't rely on the the plasma to do anything for you. And this is being pursued by a company called Proxima Fusion. There's 2 or 3 private ones out there doing this. This one is in Germany. Changing again, going back to the laser approach. And this is a company in the US called Excimer, and they've got similar to the big national laser I showed you. The laser, they've got a fusion capsule, and then they've got a chamber which captures the neutron. And this is a Excimer, and again, all of these companies are in the region of a few hundred million investment so far. There's the one of Commonwealth Fusion Systems at MIT is that's essentially got unlimited money. Now there's another one very different, and that is, well, if we don't try to go into I should say the problem with the toroidal configuration, going back to that, or whether it's a tokamak or what's happened to
your microphone isn't working.
well, it just went.
Try the other one.
I didn't do it, maybe the battery's gone flat. That is something we've had happen before. I remember that from the days I used to organise the Probus speeches.
It's just about.
I don't know whether this one is on. Maybe if you just give me the other.
Stick one.
Yeah, I think it's stick that one. Hello? This one is not working. It's not on. Oh, it's not on. Oh, it's not.
Well, that's key.
Fine. Some more energy. Okay, now, as I was saying, the problem with the toroidal configuration is very good from a plasma physics point of view. But from a maintenance point of view, it's very difficult. You can imagine trying to maintain things on the inside. I should drop it down a bit. It's very difficult to maintain. So the linear approach is better. So that has been exemplified in Zap energy, which is a linear device. So basically you take a current, and I do have a video here which I'm going to trust, which will take me to show you how it works. Here we go. It should be a button here. Hopefully it's not going to be too loud. What? What? What's going on? Turn it down.
We need to turn the sound up a little bit.
Yeah, I turn it down too far.
Yes.
I can talk you through it. Let's go back to the beginning and talk about it. Basically, what's happening here? Okay, so what happens is that we're taking a lightning strike, which they bring down. This is just an example. They don't actually do this, but this is to tell you how it works. If you put a high power current in a conductor, it will produce a magnetic field which will crush the conductor. And so what they're trying to do in the ZAP energy is rather than using a conductor, a metal conductor, they're using the plasma itself. And so that's what they're doing. They're using the plasma itself. It'll passing a current in it. It'll produce a magnetic field which crushes it, and the hope is you get to fusion conditions. And they have designs all the way up, experimental device here. And this is a repetitive thing. They bring in the plasma, they bring it down, and then they pass the current, and you get the explosion, and hopefully fusion conditions, and then you do it again, once every second or so. And they've gone all the way to design a reactor class device doing that. And then the last one is called helium, which is a similar linear device, which I don't have time to go into, but this one looks at what's particularly good is they're trying to exploit a different fusion reaction between deuterium and helium, which doesn't generate a neutron, but it generates a high energy alpha particle where the energy is. Now I want to come to the two government initiatives. First one is on the left, which is a British one, which is to take the spherical tokamak and bring it up to a reactor class device, and something like 2 billion, some big investment is expected there, and the site has been identified. And the other one is what's known as BESS, which is a Chinese device. I'll say more about that later. So the UK has got like 2.5 billion planning to invest over 5 years in the STEP program. Is to deliver fossil to fuel, fossil to fusion mission. It's part of the industrial strategy, and the site has been identified, which is just north of Nottingham, just in North Nottinghamshire. And already there's serious design work underway. The concept design has been presented. Now, the original labelling was it was going to be small, but it actually isn't. If you compare it, I made this comparison. This is the STEP device in one of their papers, and this is the ITER device. So it's not going to be small, and I don't think they're going to have anywhere near enough money, but they hope that private investment, rather like with the water companies, they hope that private investment will come in and solve the problems. Now to the Chinese device. Now, first of all, China has been building fusion devices since the 1980s. I've been going there myself since the 1980s. And this is their most advanced device at the moment. They call it EAST, Experimental Advanced Superconducting Tokamak, using superconducting magnet. And their motto is open to share. And they've got an emblem outside, a structure, open to share. And they've had many international collaborations. They've held world records in fusion. For example, they've got the world record for the longest plasma pulse. When you're used to fusion plasmas happening for a short time, they've achieved 17 minutes world record. They build futuristic buildings. That's their control building from the outside and from the inside, which I took myself in May on this design, as you can see. Somebody else who's working on there. And give you some idea where BESS fits in on the overall plan. So here is the cross-section of ITER, very big device here, and JET is down there, so you can see the step from JET to ITER. And the BESS device is roughly JET size, but with a higher magnetic field. And a little bit more about the detail. So those are the magnets, the vacuum vessel, and this building is the building which is under construction now, will be their central building. Note the central part with the torres and these two wings. That's what it'll be like and stuff. Very ambitious timescale. First plasma at the end of 2027. Fusion conditions, something around about 2030, so 5 years from now. Now the progress is phenomenal. This is a picture I took myself in December 2023. Basically, the site preparation, bulldozers running around. Note these buildings here. 2023. 18 months later, it looks like that. That is the same site. If you see those are the buildings there. And this is a kilometre or so, right? And you can see the beginnings of that shape of the building. You see that bend there, and this bend there, and the tokamak will be in there. And the buildings are that you're looking at now, are that kind of height. 18 months from a brown site to that. And then next door, they have a fusion research facility, comprehensive research facility called CRAFT, right next door. And that looks at all the high components like the vacuum vessel, the magnets, the heating systems, all the technology, the fusion technology being developed are right next door. I'll skip by that. Now, I went to a meeting there, and I want to emphasize the international aspect of this. And this little video will do it. Let's hope it's not going to be too loud. A different nationality. They planted a tree for each of us senior international advisors. And you saw a picture of me standing in front of my tree. And every time I go and water it. And, it was a really wonderful occasion. And Fusion International Friendship Garden, specially built to emphasize the international friendship approach. Now we come to that question. East and West, or East versus West, who's going to win? I'm going to define that by who's going to get to Q fusion more than one. More power out than power in. Well, the East plus West venture is basically Eton. And as I've said, it's not making good progress. I don't think. They're talking 2035, 2040 or something like that before they get to fusion condition. So that's, in terms of this argument, it's not East or West, East plus West. It's going to be East, West, East or West. Now, the East attempt, there are several fusion devices going on, fusion endeavors in China. I obviously haven't covered them, but the best, I believe, is the one that is the most advanced. And it's got a couple of positives. It's got conservative physics and technology. So it uses technology tried and tested on the East machine. It also is well funded, all the money necessary. It's actually funded by the province rather than the federal government. It's backed by a big institute. It's got that large fusion tech center right next door, and it's fully open for international collaboration. And many, again, especially Europeans, Americans have been withdrawn since January. Wonder why. And the British are on the fence. Don't know what to do, because Trump is pulling us one way. All common sense tells you to go another way. So that's case. West is the American one, which has got the American energy enthusiasm. It comes out of MIT, no better place on the planet. Unlimited funds, essentially. However, it's a closed project because, of course, it's investment. It's a private investment, so it hasn't got that wide collaboration. Everything's restricted, non-disclosure agreements, all that. It has. So there's a lot of positives there, but it does have this absolutely novel technology, high temperature superconductor to build a magnet. Nobody's built a magnet that far. I do have another video on that, but I'm not going to show it because of the time. So it's between East, the best tokamak in China, and US tokamak. in the US. And frankly speaking, it's too close to it. But the timescales are short. The Spark tokamak, the MIT tokamak got a 2-year lead, something like that. And they're talking about end of 2026, end of next year for turning on that device. And the Chinese, okay, you saw the progress. Amazing. I went down that bit. I arrived at the meeting late, so they gave me a private tour of the building site. And I said, are you still working three shifts? And because I knew they were. And they said, no, we've cut back to 2 because we're ahead of schedule. Absolute true statement. Anyway, so when we've done all that, and we've got a tokamak, and it will be one of those 2, I believe, to producing Q fusion more than 1 on a sort of 3 or 4 year timescale, maybe 5, something like that, 5-year timescale. What next? Well, I think in the meantime, there's other things being worked on. And as I've said, I think the linear devices, and I'll pick out 2, the Zap Energy Pinch and the Helion device, which I didn't have time to describe, are very interesting, are going to be more reactor relevant. And I think based on the progress and the success of those 2 tokamaks, investor money will pile in, and a good, possibly on one of these 2 things. So I think one of these could take us all the way up to a realistic fusion power reactor on a timescale of 10 years or so from 2030. So I don't know, expect some fusion power around about 2040. So with that, that's the end of my talk. Thank you.
Thank you very much, Alan. Very interesting. Everyone kept up. And first 2 questions. So we've got a couple of microphones that will come around the room. So when you're given a microphone, and ask the question.
Thank you, Alan. Could the British government be spending £2.5 billion on developing fusion in the UK?
No, my view is they should. What happened was, I didn't know, but because of Brexit, they came out of the ITER project. Which at first sight you think, well, maybe that was a good idea because of all the delays. But the other thing that's important about the ITER project was that in parallel with that, you had R&D going on in 7 nations. And according to the ITER agreement, it's a share. Everything is shared between all of them. And by walking away from the ITER project, we've walked away from that. We're trying to get back in now, you know, like we're trying to do other things in a makeshift kind of way. But we walked away from that massive R&D endeavor by 7 nations, big nations. And we're trying to go our own way. And as I said, I think when you get to the realities of that device, which I showed, it's not going to be small. Because fusion neutrons need a meter to slow down. Doesn't matter how big the machine is, they need that much, 14 MeV neutrons. So you can't actually, there's a limit to how small you can make it. I think, well, we can't even build around it, right? So how can we do this? I don't want to be too negative, but I think we should have stayed in the international and fully engaged with the likes of the Chinese device. But even to go, I have to get special visa.
The figures you quoted for the cost increase on Ethernet, from 5 billion to 25 billion, sounds pretty modest, actually. I mean, let me just think, well, which will come first and which will cost less? Achievement of commercial fusion power or the completion of HS2?
I have a daughter who lives near Wendover. I drive through moonlight, a moonlight setting every time we go to see her. It hasn't changed much. I think fusion power. Especially with the likes of MIT and CFS, full power behind it, and that Chinese endeavor.
I missed the beginning, but I guess the whole fusion reactor will have something more than petabytes, whatever, petawatts in energy. So how do you transport it away from the fusion reactor into the next, into the grid?
Well, you can do it in multiple ways, but one way you can do is just make electricity locally and put it into
I
the.
don't think you have currently such an infrastructure to take away such energy.
Well, no, the typical fusion reactor is like a gigawatt, which is roughly the same as Hinkley Point. So it's at the same power. The other interesting aspect of fusion, which doesn't apply to fission, is that the reactor is very hot. It actually generates a lot of heat. So it's actually very good at supplying heat directly to the local things like steel plants, for example. And that's one of the potential applications, especially if the devices can be made small. You can just go straight to heat, and you don't have to go to electricity. Similarly, with the town, you know, you could heat the town from the heat from a fusion reactor just by going straight to heat.
It's another.
There's another.
Sorry, thank you. You talk about hydrogen isotopes. Was any work being done on the heavy elements in that graph you showed?
Well, for fusion, I mean, the heavier elements are the ones that fission, like uranium, thorium. They fission towards going towards iron, and that's the fission. The whole fission power part is on the right hand side of the graph. On the left hand side, yes, there is boron. I did mention very briefly. There's a fusion reaction involving hydrogen isotope and boron, and the benefit of that is the fusion product is you do not include a neutron. It's the neutrons at the moment in fission plants and in fusion plants. The energy comes away on a high energy neutron, which then has to be slowed down, and you end up with large quantities of steel and water to slow it down and get the energy out of it. But the neutron passing through also does damage, and that's one of the maintenance issues you have to worry about. But there are fusion reactions between hydrogen and boron, which rather than producing a high energy neutron, they produce a high energy helium atom or helium ion. And then you've got an energetic helium ion, which you can then use to make electricity directly. So you can go from the fusion process to electricity without going through all the neutron process. And that is one of the things that's being explored by that helium device there. They're trying to explore a device and very clever mechanism. Basically what happens is you've got these magnets, you produce a fusion device in the middle, and then when the fusion device gets energetic, it pushes back on the magnets, and you end up with an electric current back in the magnets, which you then take away. Really clever, and there's no neutrons. So that works. As I say, once we get past Q fusion of even already lots of money is piling into these various options. But once it's clearly demonstrated we can generate that, which we would have done if we built the next machine which Europe had in mind, we would have had Q fusion of 1 by 2010. If the geopolitics hadn't got into it.
I'm just curious to know, I mean, there's obviously a considerable amount of investment going into it right now, but is there any future predictions that fusion might become a free energy source at some point in the...
No, it would never be free. It will obviously have a reduction of maintenance costs.
Yeah.
But at the moment, it's very difficult when you look at concepts like this, which are so sort of left field, to know where they're going to come from. But if you look, there's a lot of work's been done on the tokamaks to estimate what kind of cost there would be on electricity coming from that route, and it looks similar to other means that we at the moment we use at the moment. But something like these could be quite different.
And is there anything in science that would allow for, you know, a sort of a Iron Man type reactor?
Well,
Where you have a little thing that goes in front of his suit.
oh, no, but I can see one small enough for, say, a town like Henley to have its own on a half the size of a rugby pitch, and producing possibly just heat to the town.
Question? Thank you very much. Oh, one more.
Oh,
Obviously, all these fusion developments are the way to go long term, but at the moment, there's simultaneously a lot of investment going into small modular reactors, which of course are fission, so something we've been used to for a long time. Will SMRs become irrelevant fairly soon as fusion progresses?
No, I don't think so, but they may well be replaced by smaller fusion plants in years to come. I think we need to get our own independent energy sources ASAP, and fission power is one of them. And the thing about the small modular reactors is that they generate this possibility of being factory built, and then repetition factory built. Then you could then move the parts, and so the build time would be much less than it is at the moment. That's the hope with those.